Greetings, Earthlings. Welcome to a review and guide for the lab, the parallax method. Here I am, not really on the moon, obviously, but you're seeing the famous Earthrise picture that I showed you from chapter one. Single-handedly launched the environmentalist movement, and Earth Day, April 24th, this semester, came up and was originated shortly thereafter. So let's put this lab in a larger context. Um, and that is a basic uh, foundational piece for astronomy. If you don't know the distance, you don't know nothing. You read all the time, such and such a star, Alpha Centauri, 3.2 light years away. How do they know that? How do they know that galaxies extend out for billions of light years away? How do they know that? And it's so important because, for many reasons, uh, an obvious one, and this lab deals with this fundamental issue, is when you look out in the night sky and you see a bright star next to a dim star. The basic question there is: the bright star brighter because it's closer, or is it brighter because it's just producing more energy, like the difference between a 100-watt light bulb and a 40-watt light bulb? You can't answer that question unless you know the distances to the stars. So the larger picture of this lab is something called the cosmic distance ladder, a triumph of science to be able to devise methods for finding, you're seeing here at the last edge, 10 to the 10 light years away. Well, one light year is about 30 trillion miles. So 10 times 30 trillion is 300 trillion light years across, using the technique you're seeing there of galaxy clusters, also known as a globular cluster. You may have heard that term before. So on the cosmic distance ladder, you see here at 10 to the minus 4 light years, that's 1/10,000th of a light year. One light year is 30 trillion miles. 1/10,000th of 30 trillion miles, shifting the decimal place 4 places to the left, is whatever that number is. It's basically good. This first technique here is good for the solar system. If the object is in the solar system, all you need to do is bounce a sound wave off of the object. This is the same technique that is basically used to map the sea floor of the oceans. On a boat, you have a device called a pinger, and the pinger is affixed to the bottom of the boat. And up from the captain's quarters, you control the pinger. Hey, send out a sound pulse. The sound pulse travels and it hits the bottom of the sea floor and then returns back to the pinger. All you need to do to figure out the distance of the sea floor, how deep the ocean is you need to know the travel time, how long it took that sound pulse to bounce off the bottom of the seafloor and return back to the recorder. Knowing that time, the formula at work here is speed equals distance over time. Solve that equation for the distance by multiplying both sides by t. And so distance or depth of the oceans in this case is equal to the time it takes for the sound pulse to go back and forth and the speed of sound in water, which is a precisely known number. It's the same idea with mapping the solar system distances. Amazing, right? So you're seeing in the slide here, they're bouncing a sound wave from Earth to Venus. And there's the travel time. It's a round trip. It bounces off and returns back. You know the speed of the wave, which is the speed of light. And with those two things, you can tell the distance to Venus. Very precisely well known, strong technique here. Now we get, but that only works for a 10,000th of a light year. What if you're outside the solar system? What are you going to do? You're going to use the technique that we are going to use today called the parallax method. And you're seeing here in the picture the Earth rotating around the sun at 2 points in Earth's orbit. One, say, during aphelion, when Earth is furthest from the sun, and the second at perihelion, when Earth is closest to the sun. And that's the technique we'll be using today, but it's only good for up to 100 light years. After that, the parallactic angle, you're seeing the parallactic angle actually in this diagram. When that gets very, very small, the technique doesn't work anymore, and you need a better tool. And this is some of the latter techniques up to 100,000 light years. All you have to do, we cover this in 114, is look at the HR diagram. You look at the picture, you look at the brightness of the object, and that allows you to approximate the distance. Amazing. Nothing fancy there, just astronomers have cataloged tens of thousands of stars, and they group into patterns that relate distance to brightness and temperature for that matter. I should tell you that that technique was pioneered by a female astronomer, which we don't really hear about in astronomy, because in this class we talk about, well, 111, not 114. We talk about Isaac Newton and Johannes Kepler, and these are all males, white males at that. But this one was a female scientist known as the technique of spectroscopic parallax. Up to 10 million light years, you need another mousetrap, another tool, excuse me, and that is the method of Cepheid variables. Oh, these are stars that pulse. And based upon that, the period of its pulsing and the changes in the luminosity, you can determine the distance. This is the method that Hubble and another female astronomer were pioneering. Then we get to the Thule-Fisher relation, which relates a certain type of supernova to distance, amazingly enough. Don't really know much about that technique, to be honest with you. Probably would learn about that in graduate school. And then lastly, but not leastly, we're now at the edge of the observable universe, right? We can see and know distances up to 10 to the 10th, which is 10 billion light years away. And we're kind of at the edge of our technology here. And right at the end, we see Hubble's law. that the distance to the object is equal to the speed. V stands for velocity, the speed that the object is receding away from us in an expanding universe, divided by this parameter here, h naught, which is known as the Hubble constant. And we immediately get into controversy here. And you'll see this is in the news all the time, different estimate of Hubble's constant. Various techniques are used to determine the value of Hubble's constant, and they don't agree. They don't agree. And so because of that, we don't really know much about what is going on at the edge of the observable universe. Scientists we've got to pin down that H naught number and see if Hubble's law is really correct. But you're at the edge of research here at the end. So again, a triumph of science. So let's dive into regular parallax, not spectroscopic parallax. Those are different. So what is parallax? I believe I went over this a bit in the chapter 3 recorded lecture, but let's just do it again. Take your index finger and put it in front of your face. Close one eye, look at your index finger, open that eye and close the other one, and do that fast. Boo, 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 boo. And you see your index finger appear to move. That is parallax. The apparent movement of an object depending upon your viewpoint. So, and one more point about this index finger exercise is it tells you something very interesting, which is now do the same thing, but moving your finger further away. Close one eye, look at your index finger, open that one, close the other one, and do that fast. And you should observe that your index finger does not appear to move as much. To really convince yourselves of the parallactic effect, move your index finger now very close to your face and do the same thing. And you will see that your index finger will appear to move more. The closer your index finger is to your face, the greater the parallax. Or allow me to substitute in the parallactic angle, which with your index finger would be the angle between your line of sight from one eye and the line of sight to the other eye makes an angle, the parallactic angle. The wider the parallactic angle, the closer the object. The smaller the parallactic angle, the further the object. There you have it. So here you're seeing in this picture some closer object. This is like your index finger. This is your eyes, viewpoint A, viewpoint B. And these are the background stars. Like now, if you put like say a line of trees behind your index finger as you're doing all this. And you're seeing, if you're looking at the closer object from viewpoint A, you're seeing the background here is blue, indicating a different set of stars. And from viewpoint B, now the background is red. Red, a different set of stars. So that's how you can tell and see parallax when looking at stars, is you will see not only the star will appear, here's the parallactic angle, by the way. Not only will the star appear to move, but the background stars will shift as well. So that is what parallax is. And here's an experiment, a thought experiment that turned into an actual experiment, but something the Greeks thought of. Hipparchus, 500 BC, thought of this when he considered a sun-centered solar system. If that is true, and the sun is at the center, not the Earth, then at 2 points in Earth's orbit, here's January and July. January is actually perihelion when Earth is closest to the sun. July is actually aphelion, Earth is furthest from the sun. Notice that that corresponds to summer when Earth is furthest from the sun. And so if you consider some closer star and look at the background stars, you should see a shift. You should see a shift like you're seeing in these two pictures here. Here, the sun is on the left, here it's on the right, and the background stars have shifted. The problem is they did this. They thought of this and they looked up at the stars in January and July. They knew how long it takes the Earth to go around once. And they saw nothing. They saw that the background stars looked the same. Any nearby star didn't show any shift at all. It looked to be in the same position. And they rejected the correct answer. And that basically sets the table for thousands of years of the wrong answer, thinking we are the center of the universe. Imagine the civilization we would have if we had known in 500 BC that we're just a tiny little dot. So let's talk about the actual method called trigonometric, uses basic trigonometric relationships because we're talking about angles, and angles mean trigonometry. So take a look at this picture. You're seeing Earth orbiting the sun in June and December. And I know the last slide said that was July. That should be July, but doesn't matter. And we're seeing a closer star and the background stars, just like we saw in the last picture. And here in December is a line of sight to the star. In June is another line of sight to the star. And you're seeing several triangles here, are you not? You're seeing one a height of a giant triangle. Here, here, and here is one triangle. Inside that big triangle is two smaller triangles. One, a vertical line from June to the sun, and then from the sun to the closer star. Remember, the technique is designed to tell you the distance to the closer star. And basically, all you need to know is the parallactic angle shown here as P. Once you know the parallactic angle, that allows you to determine the distance of this part, which is the distance to the star, this long line right here, can be determined from the parallactic angle and trigonometric relationships. Who knew trigonometry could be so useful? So the units of P is a new unit called arc seconds. Arc seconds. We have arc minutes and arc seconds. Do I have a slide in here showing you what an arc second is? I don't believe I do. I believe that was also in the chapter 3 PowerPoint. Yeah, don't have that one here. But parsecs or arc seconds, excuse me, we'll get to parsecs in a minute. An arc second is just there are 360 degrees around a circle. There are 360 degrees of sky. So if you extend your pinky out, that's about 1 degree of sky. Degrees is size in astronomy. If you take your fist, that's about 10 degrees of sky. It's about the size of the moon, actually, 10 degrees of sky. Arc minutes is a smaller unit. There are 60 arc minutes in 1 degree. So take your pinky and divide it into 60 equal sections. Each one of those sections would be an arc minute. You could take one of those arc minutes and cut it into 60 equal sections, and that would be an arc second. A tiny, tiny distance of sky. Too small to see with the naked eye, obviously. But with telescopes, you can see that. Importance of technology. So the basic idea is, again, the smaller the parallactic angle, the further the star, just like your index finger moving closer and further. So I covered the historical importance. They couldn't see, they could not observe stellar parallax and had the wrong answer. Okay, so let's get into the nuts and bolts of it here. This is very similar to the slide on one of the pages of the lab. You guys should have the lab open right now. Maybe should I go to the lab? Yeah, let me quickly go to the lab to show you guys where we're at. I believe you can see that. Here we are. We are at this image diagram of the parallax method. So here again, we're seeing 2 points in Earth's orbit, and we're seeing a nearby star. Background stars, don't really care about those. And now we are taking pictures of all of the stars, a region of the sky with a bunch of stars in it. And then another picture, and I believe these are 6 months apart, right? That would have to be 6 months apart from image 1 and image 2. Well, excuse me, no. Image 2 is only 3 months apart. 3 months apart. It's 6 months apart from the two ends, December and July. And here's the middle one, which must be 3 months apart. So you're looking at here, look at image 1. You're seeing a bunch of stars. Some are big. The bigger the star, the brighter it is. Again, this lab is designed to permit you to make an educated guess by seeing the pattern. Are the brightest stars closer or not? So you're seeing a bunch of stars here in image 1, so we could call that December. And then image 2 is 3 months later, 3 months later from exactly the same direction in the sky, and we see a bunch of stars again. But the position of the stars has shifted. There's a parallaxic effect. So if you look at this one here in image one, in image two, well, you can't really see how much it's shifted here. That's actually what we're trying to figure out. But they have all shifted because of the parallaxic effect. So if we go back to the PowerPoint here, here's 3 months later, and look at this. The distance in parsecs, look at how easy it is to pull out the distance from the parallaxic angle. The distance in parsecs, a parsec is 3.26 light years. So that's about 30 trillion miles. And you see that the distance in parsecs, you're seeing D here, is just 1 over the parallaxic angle. That's it. The only caveat is that the parallaxic angle has got to be in the units of arc seconds. That's the only thing here. Arc seconds. 1 over the parallaxic angle is the distance. Pretty incredible formula. And boy, I wish I had known trigonometry was that useful back in high school. So we see here the formula, the distance is 1 over the parallaxic angle. Now, you're all wondering, how the hell do you get the parallaxic angle? Well, that's what I'm going to show you. So here's an example. You're given the star has a parallaxic angle of 0.34 arc seconds. Note the units are correct. Just take 1 over that number, and you've got 2.9 parsecs. Extraordinary. And now you're seeing how you convert here. 1 parsec is 3.26 light years. So if you take 2.9 parsecs and multiply by 3.26 light years in every parsec, you come up with that star is 9.5 light years away. And again, you could quickly convert that to miles by multiplying by 10 trillion. So 10 trillion times 9.5 is about 100 trillion light years away in actuality, if you want to put it in miles. So if we say that this whole technique is good for 20 parsecs, in other words, more than 20 PCs, the parallaxic angle gets too small and it doesn't work so well. This comes out to about 65 light years, which in the cosmic distance ladder I showed you was the limit of this technique. Here I gave a value of 100 light years, and I just told you it was 65. So we just rounded. What's 35 light years between friends, right? So here's just another example of Alpha Centauri, our closest star, at around 3 light years away. So I already told you what number you should get there. And you're given the parallaxic angle theta. There's theta right there. The parallaxic angle is given as 1.5096, and that those double lines there are seconds, arc seconds. So again, you're measuring the parallaxic angle in arc seconds. That's not what we're going to do in this lab. It is what we're going to do, but I'm going to show you how easy it is to get the parallaxic angle in a minute. So this slide, finishing up here, I mean, this is what you see in the night sky. This looks like Hubble. There's a lot of bright ones. There's a lot of smaller ones in the background. It's very similar to image one from the lab, isn't it? And again, the fundamental key to unlocking the understanding of what you see in the night sky is to be able to answer the question, is that one bright because it's close? Or is it bright because it's just got a lot of nuclear fuel and it's putting out a lot of light, like a 100-watt light bulb? And these in the background there, is that only a 20-watt light bulb? That is the question that can be answered once you know the distance. So really, I hope you people appreciate that it is a foundational piece of astronomy. So that's what I have for presentation here. Now let's get in to some of the nuts and bolts. Why do I have a white screen? Trying to go to the lab here. End slideshow. Here we go. All right, now I gotta reshare my screen here. Cannot forget to do that. All right, so here we are again, image one. At this point in Earth's orbit, call it the perihelion, doesn't matter, and image two. All right, the first thing you need to do is to print these pages out. My printer's actually out of toner right now. Otherwise, I'd show you what you need to do. I just need to explain it. You need to print these 2 pages out, and you should print out image one, image two, and while you're at it, 3. And this is the key table in the lab that you need to be able to fill out. So print that out. This one may as well. This has all the steps. And well, actually, now that I think about it, you do not need to print out any other page other than image one and image two, because you can fill the rest of these out electronically and submit it electronically. You don't have to submit your printed out pages of image one and image two. You could, I'd appreciate it. I'd like to see the work, obviously. But if you can attach image one and image two to your lab, that would be awesome. But if that's too challenging for you, all I need are the answers. So let's go through what you're going to do. You've got image one printed, image two printed. And let me see where the directions are here. In this exercise, you will determine the distances, yada, yada, yada. Print image one and image two. Compare the 2 images by carefully placing image one on top of image two and hold up to the light. You can use a cell phone here to shine a light up from the bottom. You can hold the 2 images up to a lamp. And there's a lot of different ways to do this. And you will notice that some of the stars have shifted and others have not. Those stars that have shifted are parallactic. They will have a parallactic angle. Those stars that have not shifted are too far away to have a parallactic angle. That's why they didn't shift, because they stayed in the same position with 2 images 3 months apart. So what you need to do is to take a ruler and draw a horizontal line to the center of image 1, the same star from image 1 to the same star in image 2, and measure this distance. Record that value in table 1. So here's table 1. You can give each of the stars any name you like. A, B, C, D, 1, 2, 3, 4. Doesn't matter what you call it. And so now you will label the star and tell the distance in your ruler in millimeters. Millimeters. So you've got to have a millimeter ruler. I believe your cell phone, I mean, if you're very clever, you may be able to use the distance app on your cell phone. Not sure you can do that. Easiest with a ruler. And you'll fill in these numbers here in this column in millimeters. Okay. If you have any questions about how to measure this shift in millimeters, shoot me a message. So now you're on step 3, and look at this. You convert millimeters to arc seconds by noting that each millimeter is 0.1 arc seconds. So if you're in this column, if your shift was 10 millimeters, not saying that's what it is, your parallactic angle would be 0.1 arc seconds. No, would be 1 arc second, excuse me. Chip the decimal place 1 place to the left. That's all you got to do. To convert millimeters to arc seconds, it's 1 millimeter is every 10th of an arc second. So if you had 10 millimeters, that would be 1 arc second. So I definitely have that correct. Do not want to mislead anyone. One is quickly make sure 10 millimeters times some conversion factor 0.1, and that is 1 equals 10 divided by 0.1, which is 1. Correct. 10 millimeters is 1 arc second. Not saying that's what you're going to have. I'm just doing a sample calculation. So that gets you to this column. Now, to get the distance in parsecs, I showed you that earlier. The distance in parsecs is 1 over the parallactic angle. Look at that. And you're already in arc seconds. So you're good. So take 1 over that number. For example, here, even give you a sample calculation. Let's say your parallactic angle was 0.5. 1 over 0.5 is 2 parsecs. So take 1 over this number, and that gives you this column right here. And then, as we said earlier, take your parsecs and multiply by 3.26. Because there are 3.26 light years in every parsec. Multiply this column, the values in this column, by 3.26, and you get the last column. It's supposed to show a sample unit line equation. Don't worry about that. You can skip that. Although I'd love to see your work, to tell you the truth. How did you go from one column to the next? Just give me a sample calculation there. That would be awesome. All right. Now, step 6. Estimate the smallest apparent shift you hypothetically could have measured. Translation. That is, how far in millimeters would a star need to have shifted for you to have been able to notice the shift? In other words, when you put the image 2 below image 1 and you measure the distances, what's the smallest distance you could measure in millimeters? And then convert that to parallax, and that now becomes the distance, and convert that to light years. That then becomes the limit to which the parallax method can work. Right? Does that make sense? So I gave you already two values. I showed you the 100 light year value and the 65 light year value. So you already know that your value should be somewhere around there. Okay, and the last part of this are these questions here. There are 5 questions that I would like complete sentences, thorough answers. Look at your result from step 5 above. So here is step 5, converting to light years. Actually, that should say step 6. Step 6. So you're supposed to look at your smallest measurable parallax and your distance in light years and say, what, if anything, can be said about the distances of stars that didn't move from 1 to 2? I.e., and you should start your sentence off here, they must be closer than, and give the value. Give the value. I'm looking for a number here of light years. They must be closer than X number of light years, or you could also write, they must be further away than X number of light years. So sorry about the mistake. This question is referring to step 6. And so for question 1, you should answer that based upon the values, that you get for step 6. All right. Question 2, suppose you observe the same field of stars 3 months after image 2. How would you expect the position of the stars to appear? Include a sketch if that will help you explain what you see. So you have to go back to this first image right here and say, here's image 2. What if you were 3 months after image 2, which would put you right there? What now, how would the images change? So come up with, and you should draw a sketch. You should include some of these big boys here. And how would they appear if now you were at, say, the aphelion in Earth's orbit? And I guess I would add here that from image 2 here, you're actually looking straight on. You're looking at it, it's straight in front of you. But 3 months later, you're now looking from a different angle, not straight on, but kind of, you might think of image 1 as from the bottom, image 2 straight on, and image 3 from the top. You can envision it in a bunch of different ways. But question 2 asks you to try to make a prediction about what the same field of stars would look like after 3 months after image 2. What if you were 9 months? How would you expect them to shift? And question 4, put aside the images you've been working on for a moment. So now this is a completely different exercise. Imagine that all the stars in the galaxy have the same intrinsic brightness. In other words, they're all 100-watt light bulbs. Every single one, same brightness, called the intrinsic brightness. Stars would then appear brighter or fainter, depending if they were close or far away. So if they all are 100-watt light bulbs, the bulb that's further away would appear dimmer. If this were the case, which stars would appear brighter as seen from Earth? Those with large parallaxes or those with small parallaxes? Explain your answer. So try to think about that. If you have any questions, love to know how you guys are thinking about that. And question 5, which is really the whopper, you're answering the biggest question in astronomy. Is the star brighter because it's closer, or is it brighter because its intrinsic brightness is greater? Are the results consistent with the hypothesis that all stars in the galaxy have the same intrinsic brightness? Why or why not? And give at least one specific example, and that's definitely what I'm looking for here, a specific example. So you would go back to your table here of your stars, which you have named. So, for example, star A, blah, blah, blah. And flesh out your explanations. Should include a couple of sentences here. 1 or 2 should be enough. Well, all right, people. That's it by way of a run through of this lab. As always, shoot me a message if you have any questions. All right, have a great afternoon, day, night, morning, everyone. I'll see you later. Gotta stop the recording here.